We have 80 signups for the M0 Wi-Fi. So we'll put that in the store on Monday.
And we're live.
Hey everybody, and welcome to another Desk of Lady Ada. We're going to do a pretty simple one, a fast one tonight. It's Friday night. I got to prepare for this snowpocalypse that's coming this way. Get my hot chocolate on, maybe sprinkle some salt. But before I do that, I thought I would spend some minutes with you talking about a product that's going to be coming out next week, early next week, called the Feather M0 Wi-Fi. And I know there's going to be a lot of questions about it, so I thought I'd head them off at the pass, as it were, by talking about this board and why we designed it and why you might want to use this instead of an ESP8266, or why you might want to use an ESP8266 instead of this, because they're both wonderful little boards and you may want one or the other. So let's go to the computer and I'll just go through the product page and I'll kind of just read it off, get started. So this is the Adafruit Feather M0 Wi-Fi. It is a ATSAM D21G18. That's a Cortex M0 processor from Atmel. M0 Plus. One person once said, like, don't shortchange the ATSAM 21D. It's a Plus M0. It's this little processor right here, and it also has an ATWINK 1500 module, which is this little fellow right here. And it's a 0.1 inches longer than the other Feathers, but it's still pretty much the same small size. You can see it here on a breadboard. It's about 2.1 inches by 0.9 inches. It has LEDs for on the side here and LEDs over here. Like all Feathers, it has battery charging and powering by default. You can power it directly from USB, and you can use it with all the Feather wings. And I have a ton more Feather wings that I'm designing. I designed like a whole bunch over last weekend, so I'll get prototypes soon. We have like OLEDs, NeoPixels, servos, motors, control. We're gonna add relays, 7-segment, more LEDs. We have this OLED, of course, and all sorts of data logging, real-time clock, all sorts of stuff coming out. Basically, any kind of add-on you want to have, you plug in on top. So here's the OLED, just showing it has 3 buttons, and you can display the network access. So yeah, it's got this Atmel ATSAM D21, which I'm kind of like getting into. Like I really grew up on AVRs. Like I learned PICs first. That's what I first used with the IREX board at the Media Lab, and that was my first introduction to microcontrollers. Fun fact, I actually first programmed a PIC when I was at BU, when the PlayStation mod that you would program a PIC 12C508 came out, and that was done by Old Crow. Who's
on our show and tell.
Who's on our show and tell, and sometimes shows up in the chats and is awesome, shows off his synthesizers. So luckily he introduced me to the idea of using microcontrollers to commit crimes. So that was awesome. But I used PICs for a long time, and PICs are, at the time they were 8-bit microcontrollers, and then I upgraded to AVRs, and those are also 8-bit microcontrollers. And you can do a lot with an 8-bit micro. Tons of projects are done on 8-bit microcontrollers that run at 16 megahertz. How we pretty much took a person to the moon on not much more processing power than in a lot of these microcontrollers. But I've always really wanted to play more with the ARM core chips, especially like the small ones, and I got a little bit of a taste of that with the LPC1343, which is an awesome chip from NXP. But then Atmel came out with this family, and I think they really did a good job with this chip. It's also used in the Arduino Zero, so it's got Arduino support. But all the extras, even though it's only a 3-volt processor, it's got so many great extras. And we'll talk about why that makes this board kind of useful. It has, it runs at 48 megahertz. It's got 256K of flash. It has 32 kilobytes of RAM. It's got DMA, multiple DMA, I think 12 channels. It's got 6 serial comms, which each one of those can be SPI, I2C, or UART. So you can actually have, if you really wanted to, 6 SPI ports or 6 UARTs or 6 I2Cs connections. And all supported in the Arduino IDE, which is really neat. It's got tons of I/O. It's got a DAC output, which is super cool. It's got like 12 ADCs, tons of timers, PWMs, like at the wazoo. It's got a lot going on. So I paired both these together. Anyways, if you've been interested in maybe trying out a 32-bit chip, I do suggest this chip. It's really lovely. It's got a really great data sheet. Atmel data sheets are just like, delicious. Great job there. Anyways, so this board has a battery charging over here, and then a selection diode, so it can go from USB to battery charging, whichever is a higher voltage. There's a reset button, a little real-time clock crystal here for the ATSAM. It's another nice thing. It can dynamically change speeds, like all ARM Cortex chips. So you just give it 32 kilohertz crystal, and it PLLs up to 48. And then some text. Basically, you've got this chip, and we have this FCC, CE, and TELEC or something certified module. It communicates over SPI. So SPI plus 2 pins between this chip and this module. So the Wi-Fi processing is really done here. Like all the wireless communications, the Atmel chip tells the Wi-Fi module connect to this access point, or like, hey, like send this data, but it doesn't actually do the radio transmission itself. That's passed on to the chip inside of here, which I should actually decap one so I can look at it. I saw a photo of one decapped, and there's a little processor inside of it. But it communicates over SPI. It's very reliable, much more reliable than the CC3000, so that's good. And so the real question is, because that's pretty much the first thing everyone asks is, well, why should I use this instead of an ESP8266? Because ESP8266 is a lot less expensive. It's a single chip module. Even though you need a USB to serial converter, that doesn't add a lot of cost. It's just really tough to beat the price of the ESP. The chips are like $2. And the reason is there are some situations in which you may want more processing power, and I will show one later to prove to you that there is such a situation. But most importantly, if you want to have a chip that has a ton of GPIO and analog digital converters and a DAC and DMA and SPI and I2C and UART, those are a lot of the things that you can kind of sort of fake with the ESP8266. Like SPI, of course, you can bit bang, and there's also a wire library that's kind of also bit bang, and it works pretty well. Software serial, I don't know if it's actually been ported to the ESP8266. I think somebody did, but it's going to be tough because the ESP8266, it's the chip does all the radio stuff and the processing stuff. It's a very fast chip, but its time is split up in this sort of real-time operating system where you'll be doing some processing and it will be interrupted constantly for it to go handle Wi-Fi stuff. And if you don't, the chip totally freaks out. So for example, let's say you want to drive NeoPixels. You can drive NeoPixels from an ESP8266, but you can only do I think 64 or 128 or something. It's not, which is a lot, but it's not a huge amount because you need to halt all the other processes from the chip, and then burst out your NeoPixel data, and then turn on interrupts again. But the ESP8266 doesn't like it if you do that for too long. And if it misses, I think 2 or 3 interrupts in a row, it actually just crashes or hangs. So depending on what you're doing, you may want it to have your processing split from your Wi-Fi, where the Wi-Fi management and the socket management is handled by one chip, and you are left to yourself to be able to do your own processing. especially if you need to like get ADC data at a very specific rate. That's another thing. You're going to have multiple analog digital converters on the SAMD. You only get like one, and it's only up to 1 volt on the ESP8266. Now, you're probably saying like, well, I can just add an ADC and I can add a DAC, and you can. There's definitely no reason you can't, but you might just reach a point where you're like, well, I need, I'm giving up my GPIOs to add analog digital converters, and then I need to use an IO expander, and then like I need it to be a certain speed, and like I also want to drive pixels, and before you know it, you're like, I'm actually reaching the limit of what an ESP8266 can do, and so that's why this board, which is going to be more expensive, but I think at a reasonable price, might be handy. So that's the answer for the question that everyone's going to ask, which is, why use this? So let's look at the overhead, the hover cam, because I've got both set up here. So this is just showing both. So yeah, this one has this module here, and this ESP8266 is all in one here. Kind of similar antennas though. This one has, another thing is this has native USB. So if you want this to act like a USB device or something, it can do it. This can't. It has a USB to serial converter. It can only do serial. It has a kind of interesting reset procedure. This one will not auto reset when you open up the serial port. Maybe you care about that. I'm trying to think of other differences. This has more, I think is going to have, this has sleep modes, but the sleep modes are kind of weird. Like you have to tie a pin to reset, and you have to it resets itself. There's going to be more control with this if you want to go into deep sleeps. I feel like, I haven't played a lot with it, but the Cortex-M0, it has a 32 kilohertz crystal. You can definitely drop down to very low speeds while keeping the Wi-Fi chip enabled, but maybe not active. So that's one option as well if you're looking to have more flexibility with deep sleep modes. And this has a lot of analog digital converters here, and this has nothing here. This has all these pins here that are not multiplexed with the UART or SPI. This doesn't. Also, there's like weird pull-ups and pull-downs you need on a bunch of pins. Depending on the modes, it sets the boot control. So you can't use all the pins for everything you want. Like you can't add a switch on every pin because some of the pins will put it into bootload mode. That isn't an issue here. All the pins are available. So that's a rough overview. I'm sure people will find out more about the differences as they experiment. We are definitely going to keep doing projects with the ESP8266. Like, we love this chip. But it's not good for everything. For example, Phil B and I, Paint Your Dragon, who is like, god of NeoPixels, and he's on like a mountain and he like throws NeoPixel lightning bolts on people, I think. He and I have been sort of playing around the idea for a few months now of, wouldn't it be cool if we had a Wi-Fi fade candy? Something that basically was like the fade candy from Mica, which is an awesome board, but is USB only. What if we gave up a little bit of functionality but made it wireless? And that would allow us to do internet-connected art that was portable, like wearables. Like, we've always wanted to do pixel jackets or pixel skirts, and we want to stream data to them, and if we can use Wi-Fi, that's really awesome. So we tried doing this with the ESP8266, and the answer is you can kind of sort of do it. There is demo code out there, and we played with it, and we kind of hacked it and modified it, but you can only really do 64 pixels, and you have to bit bang the NeoPixels, and then you have to go back and get packet data, and the fact that you only have a few pixels that you can use, and the fact that you have to stop everything, bit bang the NeoPixel, and then bring up the interrupts, and then you can handle more data, means you can't do stuff like dithering or interpolation, because you're spending all your time either receiving data in the interrupts or pushing NeoPixel data out. And what's neat about the AT-SAMD21 is it has DMA, and DMA is something that allows you to move chunks of memory around from peripheral to RAM or back without having to actually do the data transfer yourself. So instead of actually pushing a data out on a byte onto SPI by like SPDR equals X or SPI.transfer, you actually just say, hey chip, I have 2 kilobytes of memory over here, and I want you to move it to SPI as fast as possible and let me know when you're done. And it will go off and do that completely on its own. You do not have to do any work whatsoever other than initializing that transfer, and it will do it at like super speed. And because you can do DMA on this chip, you actually have a shot of streaming data to dot star pixels fast enough that as Wi-Fi data comes in, you can interpolate it, adjust it, do dithering, and push it out, and not be, even though this is 48 megahertz, you can have the performance of a much faster processor if it were actually pushing out every byte at a time. Whew. Okay, so let's try it out. So I'm going to remove this ESP. You're a good chip, but you're going to go over here. And I'm going to grab dot star matrix. Now you might be wondering, well, wait a minute, why aren't you using a NeoPixel matrix? Good question. The reason we're not using a NeoPixel matrix yet is DMA on the SAMD21 does not move data from RAM to GPIO. It's a little sad, but the GPIO is on a different bus, that matrix that the DMA doesn't have access to. I tried because it would have been cool. So you can't just run the Octo WS2811 type code where it does GPIO DMA. However, you can use dot stars, and dot stars just use 2 pins, but they're basically the same price as NeoPixels. You have 1 extra pin, but you can use SPI, and you can use SPI up to like 8 or 12 megahertz, which is pretty sweet because it's way faster than NeoPixels, and you get DMA, so like you get some pretty good performance. So let's wire this up. So you've got the pixels here, and then you have 5-volt and ground, and then over here you have the data. So we're going to grab some, let's see, data goes to the yellow wire, and this goes to pin 11, and then let me get a clock pin. So you get a ground wire, and then, wait, that's the wrong kind of jumper. The wrong jumper. Can I get the right jumper? There you go. No, also wrong. You know what? I mixed all my jumpers up. It's a shame. Oh, here you go. Actually, I'll use this. Okay. So there's a couple tricks that went into doing this demo. One of which is we're using a secondary SPI bus because when you DMA the data, it doesn't wait for SPI transactions. It's just streaming the data out. So so you can't use the same SPI port that the Wi-Fi module's on because the Wi-Fi module is using interrupts, and it's like using the SPI and it chip select and all that stuff. You can't be streaming pixel data at the same time to that same bus. You got to have another bus. But nice thing about the ATSAMD is it has multiple SIRCOMs, so you can just create another SPI device and then use that to transfer your pixels. Isn't that special? Get to common ground over there.
Are you going to be on the screen for a little bit?
Just another minute or two. And then I'm going to switch over to the computer. Okay, so you've got this common ground. And then I'm actually going to use a LiPoly battery to power all of this because I want it to be portable. You might be thinking, well, wait a minute, you're not supposed to power NeoPixels or dot stars from 4 volts. You're supposed to be using 5 volts. And you're kind of right, but you pretty much can get away with it, and nobody seems to care if you. One of the pixels don't seem to care if you power them from 4 volts, and the signal's 3. I mean, it's not as bright, but these are going to be so bright anyways. This wire's a little thin, but I think we'll get away with it for now. And then I want to plug this into that. Okay, so
There's a suggestion, a wearable feather wing to break out the pins for sewable connections.
it's an idea. Might just happen. Okay, so this, I don't really want to, I'll just leave this, maybe whoa. Okay, this is like not a great connector idea. I'll short out my battery. Okay, leave that there. Okay, so yeah, we've got ground, data clock, 2, 11, and 13. There's Green's clock. Yep. Power to the battery, and then common ground for data and power. That's fine. Okay, so next up, we will go to.
One quick question: are the
Yeah.
dot stars 3.3 volt IO compliant, or do they have to be within 0.5 like NeoPixels?
Well, you want it to be close to the operating voltage. So if you power these from 6 volts, which you can do, they don't like 3.3 volt logic, in which case you have to shift it up. But if you're powering it from a LiPoly, you're going to get basically 4 volts. And then your data is 3.3, and that's more than half. As long as it's about a half volt more than half, you can pretty much get away with it. I mean, if you were doing this for like a real installation, you want it to be super solid, I would use a level shifter, get a real 5 volt power supply. But
Okay.
this is the Descal 88. Descal 88 doesn't care for your logic or your good engineering. We're just going to make this happen.
Yeah, we're broadcasting from a bedroom, so
Yeah, I mean, like, there's a cat and like
There's a
some
cat right
laundry.
over there.
I mean, like,
Yep.
this is what we're dealing with here.
yeah, it's what they call gritty in the biz.
Grr.
Gritty. Okay,
Grr.
so what
Where
are
is
we
the
going to
cat,
now?
by the way?
Well, he's around.
Okay. He was on the desk. By the way, he never sits on the desk and looks at me except when we're videoing. It's like he knows. So let's go to
Computer.
the computer. Okay, and I'm going to open up this. So this is the current state of the Wi-Fi OpenPixel controller code. And again, this is coming soon. It's not done, not ready for release, but it mostly works. So yeah, this was done originally on the Wi-Fi 101 Shield, but we're going to demo it on the Feather. It uses the Wing 1500 library. It's basically a wrapper around the Atmel core. It was interesting. Atmel did a ton of work lately, and especially on this chip, they did has a really great example code. So I also wrapped up a bunch of their ASF code, the software foundation. I don't remember what the F stands for. The firmware files up, and then here's a little library we wrote just to do the DMA, just to make it easy. We create the Wi-Fi object. On the Feather, 8, 7, 4, and 2 are used. You can tell that there's an IRQ here, so it does do interrupt stuff. Your password and your port for OpenPixel control. The Feather acts as a server, and the computer is the client. And then here's where we make another SPI. So this is kind of neat. The way Atmel and Arduino structured the code, you can create another SPI device called SPI1, assign it Circom1. You have 6 Circoms. Circom4 I know is the default SPI, and then like there's there's 0, 1, 2, 3, 4, 5, and one of them is taken by I2C, one of them is taken by SPI, and one of them is taken by the default hardware serial, but the other 3 are available, so you can have an extra 3 devices. This is the names of the pins that we're going to be attaching it to. You can select with muxing which pads you want to use. And then how many LEDs we want to be able to process, 52, and then there's this math because we have to like make the SPI buffer a certain size. And then we have 2 buffers because we double buffer. When one is being DMA'd, we're filling up the next one. Because we're going to do dithering and interpolation, we have to be able to modify the buffer and then get it ready and then send it out. But like you don't have time to do that if you're actually having to sit down and like transfer each byte. Instead, with DMA, you do one, and then you do one transfer of basically 2 kilobytes of data, And then at the same time, you're setting up the next one. And then we have some flags if you know which buffer we're using. This is the payload. So this is where like having 256K of flash and 32K of RAM is awesome. So we're just like allocating 4 kilobyte buffers like all over the place in SRAM, and it's just like totally fine. After having to live with the 2K Arduino Uno buffer for so long, it's kind of joyous. Just be like, 512 pixels, and I want 3 of these buffers. Yes, and get me cake. So it's great. So you get that, and then there's gamma correction, dithering tables. There's color ordering. I don't remember which RGB. I think these are GBR. I don't remember. And then there's a little DMA object. There's the callback. The DMA library will call a function when DMA is complete. And then there's the gamma correction. Gamma just makes the pixels look better because you'll notice, if you PWM pixels, which the neopixels and dot stars are PWM linearly, your eyes perceive them to be very, very, very dim and then incredibly bright. So it kind of helps linearize that a little bit more. Okay, so then we start up, and I will have it pause until we open the serial console. It opens, basically says, okay, I'm the OPC server. It connects to the Wi-Fi network. It clears out the buffer, sets up the gamma table, initializes the SPI bus, and then this is where you're actually doing the fun DMA stuff. So I'll do some tutorial later about this DMA library because it's really fun to play with DMA. It frees a lot of time in a lot of processing, like analog digital conversion or digital analog conversion or moving data around, or like especially SPI where you're like, okay, I need 512 bytes from my SD card. Instead of waiting around and doing one at a time, you can just DMA it. So for this, you can configure what you want to use as the trigger, like what tells the DMA to continue on. And in this case, it's SIRCOM1 DMAC IDTX. Basically, when the last byte from SIRCOM1 has finished transmitting, send the next one. And it's like, what do you do? And it's like, we'll just send, this just means send 1 byte at a time. You have to allocate it, add the descriptor. You can have 12 descriptors or something. Register that callback, so that's that function that gets called when the DMA is complete. And then you enable it. In this case, the DMA is set up, so only 1 transfer of 2 kilobytes is done, and then it calls the callback and it says, hey, I'm finished. You can link DMA descriptors together. So you could, for example, if you really wanted to, let's say you wanted to transmit the same buffering over and over again. Let's say you didn't want to do double buffering. Let's say you want to do double buffering, but you don't want to have to kick it off. What you can do is have one descriptor that reads data from one chunk of memory, and then another descriptor that reads from another one, and link them to each other. So when one is complete, it calls the next one for you, and vice versa. So they go in a loop. You have to kind of watch out and make sure that your buffers are ready, but it is possible. And then, where did we set up the DMA locations? Oh, you know what? We do that later. Never mind. Okay, so turn off the LEDs, and then connect to, check if we were connected to Wi-Fi while we were waiting. If so, just say we're listening. And then there's interpolation called magic, and this is what takes 2 buffers and makes I think a third one, where it interpolates between the 2. So this gives you smoothness between frames. And this is like Philby. This is the stuff that Philby does. I'm not good at that stuff. And then here's the kind of interesting stuff. So we have a flag that says, is that previous SPI DMA transfer done? And if not, just wait around, finish. And then when it is completed, you set up the next transfer. So from the fill buffer, send it out to the SIRCOM1 SPI data. So basically, it's just going to move 1 byte at a time. The entire buffer size, 1 byte at a time, and then increment the source address. So instead of just the first byte from fill buff, it'll go fill buff, and then fill buff plus 1, plus 2, plus 3, plus 4 to the end. And then don't increment the destination. That's because we always want to write to this register. So that memory location is, all the data is moving to that register. Don't increment, don't move forward, otherwise you'll start overwriting all sorts of stuff. and then you can set up your SPI transaction and then kick off the DMA. That's pretty much it. Like it just runs in a loop. Like every time
Do
it
you want to
gets.
answer some questions?
Yeah, sure.
Okay. Does waiting for DMA defeat the point of DMA? And how would you compare this to the ESP 8266?
So the waiting for the DMA does not defeat the purpose if you have already finished all the processing that you want to do while the DMA is going on. So for example, the OpenPixel controller, you can set how many frames per second you want to push data. If you're pushing 60 frames a second, you're not going to have a lot of time between each DMA transfer. Also depending on how many pixels. But let's say your pixel count is small and you're doing 30 frames a second, there could be a few milliseconds while you're waiting. So you've already transferred your data, you've processed it, you've done your gamma correction, everything is ready, you've done an interpolation, and you're doing your dithering, and you're waiting for the next transaction. It's not a bad thing. It's always there if you want it. You don't have to wait, but like you still have to have certain things occur at certain times. And on the off chance that you are getting data faster than you can process it, you have to wait for the DMA to complete.
Okay. The nice person in chat said, good point. All right, next up. How would you compare this to the ESP 8266?
Rewind like 10 minutes because I talked about it for 10 minutes.
Okay, so...
I'm not going to do it again.
So,
but it's in the video.
all you have to do is wait till YouTube posts a full video and just scrub to the beginning.
Yeah.
There you go.
I
This
just-
is cool because when we get asked in the future,
I already did it.
We'll have that link. Okay.
I know people showed up at
That's
halfway
great.
through.
Yeah, that's fine.
Okay.
Next up.
Sorry. We just already covered it, but I want to keep moving.
Let's keep moving.
Keep moving. Okay.
Tell me
so-
when you're ready for questions again.
Yeah, basically, like I'm not going to go to the detail of this because it's basically you're getting payloads, and there's all sorts of OPC data. This is where the data is actually read in. So let's just run it. I'll be honest, I wrote some of the DMA code, but I didn't write the OPC client code, or the OPC server code. That's Phil B. If he wants to do a stream, he can.
Yeah. So you're split screen right now if you want to move anything around on your right-hand side.
Yeah, what I'm going to do is I'm going to upload this code, and then I'm going to get rid of this window.
Yeah, but you see what I'm saying here?
Yeah, no, I'm going to, this is going to be here. I'm going to upload the code, get it so it's receiving, and then I'm going to move the, this takes a while to compile. Okay, it's uploading. Okay, done. Okay, okay, cool. So this is my OPC Wi-Fi. It's listening on 10.0.157, port 7890. So your computer that you're using to connect to has to be on the same network, by the way. Like, in theory, you could NAT this, but it is a direct server-client connection. So, and you can't use Adafruit I/O for this. Like, you have to have there's a lot of data being transferred. So next up, let's open up processing. And that's what basically Fade Candy and OpenPixel Control uses. You can use anything else, but it's a very nice, elegant way to do the demo. And I already tried this out, so let's do wave fronts. So when you open up this demo, you have to set up the OPC, and so make sure it has the same IP address, 10.0.157, because the MAC address is like registered now, so it's always going to get this location. And then you want to set up the grid size. So by default it's 8x8, but I want 16x16 because I have a full 16x16 pixel array. And then the last, this is centered, width divided by 2, height divided by 2, height divided by 20. That's the dot distribution. You'll see that. 0, I don't remember. Oh, this is angle. This is no angle. It's going to be a square grid. And then true because the destination is zigzagged because the pixels go in a zigzag. If I set this to false, it would be weird. So let's...
A nice person in chat called The Game of Knowing says, I feel like the Feather series is going to change the Arduino compatible space a lot within the next 6 months. These boards are freaking awesome, and our response is, we think so too.
Yay, thank you. I'm spending a lot of time on them, so I'm glad. I mean, and I have been working on them for 6 months, so it takes a long time. We have some more really exciting ones coming out soon. more Wi-Fi options.
Boards of a feather is what we like
Boards
to say.
of a feather. Okay, so let's click play. So over here we see this is saying getting updates, and then on the overhead, let me turn off the.
You can also extend out on the other overhead if you want to.
Yeah, why don't we extend out so we can see more? And then I will, hold on, just give me a second. This hovercam is cool, but I have to just get things centered. So you've got pixels going. Oh, that actually kind of makes a cool, look at it, like, it looks like it's coming out of the display. So yeah, so this is just the demo of data being transmitted from the computer through the router to this. And if you can see a little bit, see these little sparkles? So you can see that there's this dithering and interpolation going on. Especially, yeah, like at the end you see it a little bit more because it's really fading out. But what the code is doing is it's trying to mimic a higher resolution video, higher color resolution display by, because this is only 8 bits per color RGB, which is 24-bit color, which is pretty good, but it's not good enough because you still have to gamma correct it, and so you lose a lot of your bits. So what it does is it turns the LEDs on and off really, really fast so that it appears as if they're have a wider dynamic range, not resolution. Okay, we're gonna take a 3D photo. Whee! Yeah. So yeah, this is a nice little demo. So you just move your cursor around. But so this means that you can use any of the Fade Candy projects, and you can basically do them over Wi-Fi. Now, it's not done. We're still working out a couple of little bugs, but it does work. And I thought it would be neat to show on the scope cam before we wrap up the DMA, because I want to show how cool it is.
Okay, we're on scope cam.
Okay, 1 second. I have to get my my jumpers. I'm just having a little bit of a jumper crisis here. Okay, so this is, clip this to ground, and then, yeah, I will. Just sorry. Let me get the. Oh man, I keep picking up the male to female jumpers instead of the right kind of jumpers. This is the right kind of jumper. Okay, I will adjust in a second. Okay. So this is the output of the SPI clock for the dot stars. And it's 8 megahertz. You can run it at 14 megahertz, but, sorry, at 12 megahertz. Actually, you can do 24, but the dot stars don't like it. You can't drive a large number of them at high frequencies. And what's interesting is you can see how there's no gaps? So if you were doing normal SPI, like pushing through, even if you're using SPI transactions, you would still be like sending 1 byte, and there would always be a little bit of a delay between bytes because you'd be loading up the next memory address or incrementing, or like there's a for loop, or something. There's always like a couple of instructions between the first byte and the second byte and the third byte, which isn't a lot, but it does add up. But what's really neat is with DMA, it's like this beautiful, clean square wave that just goes on for infinity. It's perfectly timed. The moment one SPI transaction is done, the next one kicks off instantly. And it's all done for you. And then we can see, I mean, it's pretty much streaming all the time. Wow, there's really like no gaps. You can see there's once in a while there's a teeny bit of a gap, but pretty much it is running 24/7 data transfer. So that's kind of neat. I don't know. I kind of like it. Anyways, so the next question is like, well, you can do dot stars, but is there some way, even without GPIO DMA access, to DMA write NeoPixels? And there might be. We're going to explore some possibilities. maybe do another Desk of Lady Ada with our findings. Depends on if we get snowed in. If we can't go outside, we might as well stay in and hack some code.
Edward Snowden is in Russia. He won't be here tomorrow.
What?
Sorry, I wasn't paying attention.
Okay, I meant the snow from the sky.
Snowed in. Oh, not Snowden. You mean Snowden.
Yeah, look. I'm trying to chat up Snowden, but he just doesn't want to come on the show.
No.
Anyways, that's the show.
Okay. Do you want to answer a couple questions?
Yeah, sure.
Okay. Will you make a feather with a high voltage relay on it?
Yes.
Okay.
I will. I can show that off if you go to the computer.
Whoa, that was fast.
Well, I didn't design it now. It was already done.
Oh, okay. I was
But
like,
I can.
jeez,
But
man.
I can show it off. Let me close down processing.
All right. Well,
So.
you asked for it. Here
wait,
it is.
Hold on. Because I did last week. I was under relay. I have two kinds actually. So I have a latching version, and it uses it's a 2 amp only relay, but they're really, really small and cute, and it can do 250 volts, and then the terminal blocks over here, and then there's the switching protection, a little LED, and then you can set and unset. And so the nice thing about latching relays is that you don't have to hold the coil on. Like you have to like click it to set and click it to reset, so you have 2 pins that you have to use, but you don't have to use any power while it's switched from one or the other because it latches open or latches closed. You only have to use power to switch it from closed to open. So that's that one. It's only one relay, but I couldn't really cram 2, and I wanted to keep things, especially in the high voltage area here, I wanted to keep it sort of spaced out. And then I also have I have a non-latching one, a little simpler. It only, has a little bit more circuitry, only one signal pin. I might have been able to fit 2, but it would have been a squeeze, so I only fit 1 in. And but yeah, it's also a 2 amp, 250 volt relay. So I don't like relays. I really hope nobody does something stupid and hurts themselves with it. I will put lots of warnings, but I do see people using it for 24 volt stuff. For 24 volt stuff, like that's cool. Like people want to have it control some home automation or some car stuff or battery, like high power battery, or they want to use it for like a doorbell or garage door opener. That's fine. I always get nervous when people start like splicing mains wiring. I don't think it's a good idea.
Okay, so since you brought out a scope, folks want to know what scope could they get started with if they're thinking about getting a scope?
Oh, if you're just getting started, so what's neat is like I got this tech scope, the one that's on my desk here. It was like my pride when I first started Adafruit. I was like, I have money, and I'm going to invest in the company, so I'm going to buy myself an oscilloscope. It was $2,000. This 4-channel color scope was $2,000. Now it's a great scope. I love it, and I use it every day still. But nowadays you can get like a Regal scope or an ON scope for like $400, and it pretty much has the same specs. Like it doesn't trigger quite as nicely, and it's a little louder because there's a fan. It's not as low. It's a lot of low noise, but for just functionality, those Regal scopes, like they're awesome. And we're a Regal distributor, so I'm only saying that because I wanted to become one because their scopes are so good, but there's also tons of competitors to Regal that make good scopes. But any of the 100 megahertz color 2 or 4 channel ones, a couple $100, and like I remember people used to say like, oh, get it used tech on eBay. And nowadays I'm like, it's gonna show up, it's gonna be broken. They're really heavy and they're annoying to ship. They break, and like just get an LCD scope. Super, super easy.
Okay, we haven't announced any pricing for the M0 Wi-Fi, so there's nothing to.
There's nothing to talk about, but I will on Monday.
Yeah, Monday.
We're still debating
Yeah.
the price. We want to make sure we have a good price,
Okay.
but it will be affordable.
Does this support debugging?
Yes, it does. You need a SimSysTap debugger, but there are 2 pins on the bottom of the Feather. I haven't actually done debugging on the Feather. I've done it on the Zero, which has the SimSys that built in, which is the eDebug chip. But let me see, feather 0. So on the bottom, actually, you know what? I will show it on the on here rather than on the.
Okay, and then last question.
Yeah, over
for the
here.
night
So
will
sorry,
be-
this is the these 2 pins here is the SWD clock and data. Connect those and ground and the reset pin to your Simpsons Staff Debugger, and you can use Atmel Studio, and it's awesome. I've used it a bunch, and it's very, very handy.
So last question request. Will you publish a template for the feathers?
There is in the, well, there's one thing you can do that's really easy. If you go to GitHub, and I'm pretty sure I put the feather wing. Okay, so go to the Featherwing Proto and Doubler, and you can download the board file for the Proto Featherwing. And honestly, the fastest way to get started is to grab that and then delete all the proto holes, and then just put in the circuitry you want. Because that way you get like all the holes in the pads in the exact right location. That's the easiest thing you can do. I think I added to the Eagle library the feather as well. Let me check. Yeah, I did in November. So in the Adafruit Eagle library, there's also a board object file for Featherwing that you can use to create your own feathers or feather wings.
Okay, and that's it for tonight.
Yay!
Thank you everyone for joining us on the Desk of Lady Ada. If you want to support Adafruit and this type of programming and this type of content on the internet, just pick up electronics in our store, adafruit.com. That's all you got to do. We don't have ads, loans, venture capital, none of those things. We're completely independent, supported by you, our viewers.
You don't get a mug, but you will get electronics,
Not
which is
yet.
way more useful.
So with that is the Desk of Lady Ada.
Okay, thanks everybody. Hope you guys had fun. We'll get back into more engineering shortly.
Yeah.
And this demo is coming soon. Don't ask. Phil B is working on it. When he feels like it is beautiful and ready for the world, it will be released, and you can make your own wireless pixel controlling going on.
All right, and we'll probably broadcast again over the weekend. Maybe we'll stick a camera out the window for a snowpocalypse.
Yes.
All right.
Snowtronics.
Good night,
Okay.
everybody.
Bye.